Hello, I'm Martin Looker from Silicon Labs. In this dev lab, I'll be using CircuitPython on the secure connected EFR32MG24 wireless microcontroller to create a Bluetooth Find Me application. This is the kind of device that you might attach to your keyring to help you find your keys if you were to misplace them around your house. When running in idle mode, the device flashes both LEDs briefly once per second. We can connect to the device using Bluetooth from the EFR Connect mobile application. Once connected, we can open the immediate alert service in the device and write a value to the alert level characteristic. Let's write a mild alert. As you can hear, a tune is played while the alert level is set, and LED 0 also flashes rapidly. The alert can be cleared by remotely setting the alert level to none. The alert level can also be set to a high level to play a different tune and flash LED 1. The alert can also be cleared locally on the device by pressing any button. Code is also present to trigger alerts from one device to any others that are in range. While a device is in idle mode, button 0 can be used to swap the device to Locator mode and set other devices into the mild alert state. While in mild Locator mode, LED 0 will be on with a brief off period once per second, and pressing any button on the Locator will cause it to attempt to clear any alerts that have been set before returning to the idle target mode. During this time, both LEDs on the Locator device are permanently on. Button 1 works in exactly the same way, but will instead trigger high alerts, and this alert is indicated on LED 1 instead of LED 0. Alerts can still be cancelled on the sounding device by pressing any button. The Bluetooth implementation follows the standard Find Me profile as defined by the Bluetooth SIG. The Find Me profile specification defines two profile roles. First is the Locator role that can be used to trigger alerts in devices running in the second target role. The target role is used in a device to be located, and alerts are triggered through the immediate alert service, which has its own specification. And this contains the alert level characteristic, and you can see the GATT specification supplement for details of this characteristic, including the values that can be written. The device created in this dev lab is able to operate in both roles, as we saw in the demo a moment ago. I also used the EFR Connect mobile application in the Locator role during the demo. You can find links to these specifications in the video description. To follow along with this dev lab, you can use any of the 3 MG24 boards that support CircuitPython, plus a passive piezo buzzer to play tunes. This could be skipped as alert levels are also indicated by LEDs. The easiest board to work with is the Silicon Labs XG24 Explorer kit. This comes with header sockets fitted to form a microbus connector. By adding pins to the piezo buzzer wires, you can simply connect it to the ground and PWM pins on the header socket. This board also has the 2 buttons and LEDs that are also used by the application. However, this board does not provide an easy method to power it from a battery, which makes it less portable. The second board is the Silicon Labs XG24 Dev Kit. This board does not come with header sockets, but you can easily add some to the expansion holes on each side and connect the piezo buzzer to the ground on pin 1 and the GPIO on pin 10. Or you could solder it on directly. This board also has the 2 buttons used by the application and an RGB LED, and use is made of the red and blue channels here instead of 2 separate LEDs. In addition to these, there are many sensors fitted directly to the board, making it a great prototyping platform for many different types of applications. One advantage of using this board is that it has a slot for a coin cell on the rear and also a connector for a rechargeable battery, making it more suitable for portable use. The final board that is compatible, but requires more work, is the SparkFun MGM240p Thing Plus. This board only has a single LED and no buttons, so you'll need to add a second LED and 2 buttons in addition to the piezo buzzer. You'll find the breadboard wiring for this in the GitHub repository that accompanies this devlab, and the prototype board setup I will use in this video follows the exact same wiring. This board also has a connector for a rechargeable battery. There are links to further information on all these boards in the video description. Once you have one or more boards to work with, you'll first need to download and install CircuitPython onto them. The Quick Start CircuitPython for EFR32MG24 video will walk you through this process and also introduce the Thonny Python IDE that I'll be using in this video. To access the source code for this devlab, you will need to download or clone the Silicon Labs training examples repository from GitHub. From here, you can use the code drop-down to clone the repository using your favorite Git client, including GitHub Desktop, or simply download a zip with all the files. The files for this video can be found in the devlab CircuitPython Bluetooth Find Me folder within the repository. In the README, you'll find instructions on the operation of the application and also wiring diagrams for each of the supported boards. Links to the Quick Start video and the GitHub repository are in the video description. I'm going to divide this devlab into 4 steps, and there is a folder with the code for each step in the repository. In step 1, we'll use some basic code to make sure all the hardware is working. These are the LEDs, buttons, and piezo buzzer. In step 2, we'll make use of the hardware to create a device that supports only the target role, and we will be able to set alert levels from the EFR Connect mobile application. In step 3, we'll add support for a simplistic locator role, which will have some shortcomings in how alerts can be cancelled. Finally, in step 4, we'll address that by adding the ability to cancel alerts remotely from the locator device. Let's begin step 1 and see how to control the hardware devices in isolation. I'm in Thonny viewing the training examples repository I downloaded from GitHub. If this Files tab is not visible in Thonny, you can view it by selecting the View Files option in the menu. At the moment, I'm not connected to a board, so there is no board file system in the display. The main reason for using Thonny is that, unlike some CircuitPython boards, the MG24 boards do not mount to a drive when connected to a PC. Fortunately, Thonny provides a GUI that can be used to transfer files between the local file system and a connected board. We'll see it in action shortly. You'll find the files for this devlab in the devlab CircuitPython Bluetooth Find Me folder within the repository. I'll double-click it to open it at the top level. Once we are in here, we have 4 folders that begin device root. The code for step 1 is in the device root hardware folder. So let's take a look. In CircuitPython, the code.py source file is where execution begins when an application starts running. So let's start there and work our way down through the other modules. As you can see, there is very little code here. First, the app class is imported from App.py. An instance of the app class is created. Then we have a loop that runs while the onClass member is set to true. And each time round the loop, the app class's main function is called. From this, you may gather that the bulk of the code for this application is in App.py. I prefer to work this way in CircuitPython because it leaves code.py unchanged while creating software and avoids any issues that might occur from editing code.py in place but forgetting to refresh it. I won't spend any more time here. Let's take a look at the more interesting App.py file. This begins by importing various modules. We have the standard board core module, that contains data relevant to the board the application is running on, and we'll be using pin names from here shortly. Then we have three modules for controlling hardware: button, LED, and piezo. The first two use digital I/O to handle buttons and LEDs, and the third uses PWM I/O to drive the piezo buzzer at different frequencies. Next is RTTL. This acronym stands for Ringtone Text Transfer Language. This is an old text-based format for defining monotonic ringtones for mobile phones. This module takes care of playing these ringtones using the piezo module to sound individual notes. You'll find links to the RTTL format definition and to thousands of examples in the video description. Finally is the tick module. This provides simple polled millisecond timers that we will make use of in the application. It is also used by the RTTL module to time note durations. The code for these application modules can be found alongside code.py and App.py. I won't be going into how these application modules work internally. Most of them are straightforward and you can examine them at your convenience, but we will see how their APIs are used to create the running application. Then we have a single constant for the rate at which LEDs will be flashed on and off, 100 milliseconds in this case. Then, just after the definition of the app class, we have the initialization function. A single parameter is passed in here to set whether the module should output debug information to the serial port. The on member is initialized to false. If we fail to initialize the hardware, this will be picked up back in code.py. The main loop will not run and the software will exit. Then we get into initialization, depending upon the board that is being used. If a supported board is being initialized, the on member is updated to true, and then the button, LED, and RTTL classes are created and stored in a dictionary. All of these initializations specify the pin the class should use for the button or LED or piezo buzzer. And for the button and LED classes, you can also set whether the operation is inverted, and so use a low signal for active rather than a high signal. The last parameter in all of these is a debug flag that controls whether the module outputs debug messages to the serial port. For the button and LED objects, there is both a high and mild button and LED, corresponding with the alert levels that can be set in a Find Me device. If the hardware is initialized successfully, a tick timer is created to drive the LED flashing. The parameters here are a name for the tick timer, which is only used when debugging, the period of the timer in milliseconds. This can be 0 if the timer doesn't need to run right away. A repeat flag, which sets whether the timer should run again automatically after firing. And the final parameter is another debug flag for the module. Finally, a dictionary of data used by the application is created, including data to control the flashing of LEDs. We'll see these in use in a moment. The final two values here are returned by loading a high and mild level RTTL tune string into the RTTL module. This load function converts the text definition of a tune into a sequence of frequencies and durations that will be sounded on the piezo buzzer when the tune is played. The load function returns the tune name extracted from the RTTL string and is saved here for playback later. The processing for the application takes place in the main function. This is called repeatedly from the loop back in code.py. First, a check is made that the application was properly initialized and so is able to run. With that check out of the way, the two buttons are read with a call to the read function. The button class includes members that will be set if the button state has changed since the previous call to the read function. There are pressed and released members that can be checked, along with changed and on members. This mechanism is polling the buttons once each time the main app function is called. There is no debouncing, it's just a straightforward polling mechanism. If the mild button is being pressed, the RTTL class is checked to see if the mild tune is not already being played. If this is the case, the RTTL play function is used to play the mild tune and repeat playing when the end of the tune is reached. The bit masks that control LED flashing are updated to rapidly flash the mild LED and turn off the high LED. If the mild tune is already being played when the mild button is pressed, the tune is stopped using the stop function, and the LED bit masks are updated to flash both LEDs briefly once per second. Then there is a set of almost identical code to handle the high button, but this time manipulating the high tune and the high LED. Next, we have a call to the R.tl main function. This is what drives the playing and stopping of R.tl tunes. The R.tl module makes use of both the piezo module to sound individual frequencies for each note and a tick timer to time the duration of each note. The main function can only start a new tune or stop a tune at the end of each note. So if a long note is being played, there may be a delay until the new instruction takes effect. The final chunk of code in the main function is based around the LED tick timer. First, the tick timer is read. This checks the current system time against the duration that has passed since the timer was started. As a result, the tick timer is polled, and there may be small inaccuracies depending on how frequently the app class's main function is called. But for this application, the polled timer is good enough. If the LED timer has fired, then the process of updating the LEDs begins. The LED flashing is controlled by a 10-bit bit mask for each LED, and a single bit is shifted every 100 milliseconds when the timer fires, resulting in a 1-second period with 10 on or off periods of 100 milliseconds. First, the cycled bit is checked to see if it has gone out of range. If this is the case, it is reset with a value of 1 for bit 0. Next, the corresponding bit in the high mask is checked, and the LED is turned on or off using the LED class write function. This code is then repeated for the mild LED. And finally, the cycled bit is shifted, ready for the next time the tick timer fires. In this first step, we've set up the application so the hardware is exercised in a similar way to that used in the final version of the application. So let's transfer the files into a board and make sure it is all working as expected. I've connected my Explorer kit board with piezo buzzer to my PC using USB. To connect to it from Thonny, I need to use the Tools, Options entry in Thonny's menu, and in the Options window I need to select the Interpreter tab. Check that CircuitPython Generic is selected in the top drop-down, then select the appropriate COM port in the Port drop-down and click OK to connect. You should see the device output version and board information in the Shell tab, and also the REPL prompt. Also, in the lower section of the Files tab, you will see the files that are in the board's file system. This is a brand new install of CircuitPython on the device, so these are the default files. To transfer files from the local file system, select them in the upper part of the Files tab, right-click and select Upload to Root. You'll be prompted if it needs to overwrite files, so click OK to continue. Once complete, we can see the files on the device in the lower panel of the Files tab. As I'm now going to work with files on the device, I'm going to close the Open Files in the editor and open the code.py file directly on the device itself. To run this open file in Thonny on the device, just click the Run button on the toolbar. Once it runs, we can see the debug output in the Shell panel, identifying the application and that initialization has been successful. Here it is running on my desk. We can see both LEDs flashing for a 100 millisecond period once per second. Pressing button 0 starts the playback of the mild tune we have set and rapidly flashes LED 0. Pressing button 1 swaps to playing the high tune and flashing LED 1. Pressing LED 1 again stops the playback and returns the LEDs to idle flashing. Now we are at the end of step 1, we can be confident that the buttons, LEDs and R.tl hardware functionality is working as expected. So we can continue to step 2 and add Bluetooth functionality to make it operate as a target Find Me device, adapting the use of the hardware appropriately. I'm back in Thonny, so let's go up a level in the local file system and open up the files for step 2. We'll start by looking at the new files for this step. First, we now have a lib folder. This is where you can add additional library modules, either ones you create yourself or ones you can download either from Adafruit's CircuitPython library bundle or elsewhere on the web. In this case, I have the Adafruit BLE library in my lib folder. This is taken from Adafruit's CircuitPython library bundle. I've included this library in the GitHub repository for the dev lab, so all the code you need is kept together. If you feel a need to ensure you have the latest version, you can download the latest bundle file and update it from there. As indicated by the name, this library provides Bluetooth features for a CircuitPython application, and we will see how it is used when we move on to the App.py changes. My personal preference is to keep modules written by others in the lib folder and the modules I've written in the root folder. In this way, I know which modules I may potentially want to download updates for in the future. But there's nothing stopping you placing your own modules in the lib folder too. In this application, the button, LED, and other helper modules are candidates for this, as is the App.py file. As I say, the arrangement shown here is simply my own personal preference. The other new file is the immediate alert service.py file. This file is used to define the main Bluetooth service our application will use, and we briefly looked at the specifications for this during the introduction. This module is pretty straightforward. First, a number of classes are imported from the Adafruit BLE library. Then a class for the service is created and assigned a standard 16-bit UUID. The values to be used for standard services and characteristics can be looked up on the Bluetooth SIG website. Next, the single alert level characteristic is created, and once again its standard 16-bit UUID is assigned, and also the access properties for the characteristic are set. Finally, in the initialization function, the service is configured as connectable. You can construct other Bluetooth services in a similar way, including ones that make use of longer custom UUIDs. You'll find many examples online, and there are a few included in the library bundle that you can reuse or adapt as a starting point if you create your own. Next, let's take a look at the changes to the App.py file to allow it to operate over Bluetooth in the target role. First, we import some classes from the Adafruit BLE library. These are the ones that we'll need to make use of in App.py. We also import the immediate alert service class we looked at just a moment ago. And before we get into the code proper, we also add some constants for each of the alert levels used by the alert level characteristic. We have some changes to the initialization function next. First is a simple change to the initial debug message so we know which type of device we are running from the dev lab. Code for initializing the app's hardware and data is unchanged, but we add a new dictionary here to hold the Bluetooth data and objects we'll be working with. First, we have a local flag in the app class to track changes to the connected state of the Bluetooth device, and also a local copy of the alert level to track changes to that characteristics value. Both of these values are also held in the BLE and service objects respectively. Next, the Bluetooth radio and immediate alert service objects are created, followed by a services advertisement class that will advertise the immediate alert service in addition to standard advertisement values, and the short name and connectable flags of the advertisement are set. Finally, the generated short name is output to debug, so you can recognize it later when you're scanning. Next are the changes to the main function to allow operation over Bluetooth. This begins as before by reading the buttons. In this step, the buttons are only used to cancel an alert. First, we check whether either of the buttons has been pressed. If the alert level value stored in the service object is not already set to none, then it will be set to none. Note that this is the value held in the characteristic within the immediate alert service object. It's not the value held in the app class, which is used to track changes. This change in the immediate alert service value will be picked up later and acted upon. Next, we have a block of code that compares the connected state of the BLE object with that held in the application class. If it has changed, the value in the app class is updated and a debug message is output. So here we're essentially polling the BLE radio to find out whether its connected state has changed as far as the application is concerned. The next block of code manages the transmission of Bluetooth adverts. If the device is not connected and also not advertising, then advertising is started. Similarly, if the device is connected but still advertising, then the advertisements are stopped. These Bluetooth advertisements allow a scanning device to discover the advertising device, including the main services that it offers. In this way, a scanning device can choose which devices to form a connection with. Next, we deal with changes to the alert level characteristic, either remotely from a connected device or locally when an alert is cancelled by a button press. If the value in the characteristic object has changed, the new value is transferred to the value held in the app object. If the alert level has changed to a high alert level, the LED masks are updated and the high tune is played by the RTTL object. Similar code handles a change to a mild alert level. The final block here handles a change to an alert level of none, returning the LEDs to their idle flashing pattern and stopping any RTTL playback. Just like with the connected state, we are essentially polling the characteristic value to determine if it's been changed and then reacting to that change. And that's it for changes in the main function. The RTTL class and LEDs are driven as they were in step 1. That's also it for the other modules we talked about in step 1. Those are the buttons, LEDs, piezo buzzer, RTTL and tick timer are all unchanged, as is the starting code.py file. I'm going to make sure that my running device is now stopped, and then I'm going to select all the files just like I did in step 1, this time including the lib folder, right click and select upload to root. Once again, I need to approve any overwrites. I'll close the files open from my local file system that we've been reviewing and open up the code.py file from my target device once again. I can now click the Run button to see it in action. The shell panel displays the updated initialization message, confirms initialization of the board, and outputs the short name that we will be using in the Bluetooth advertisements. We can also see that it's picked up and started advertising already. We can see the board running in the idle mode on my desk, and also the EFR Connect mobile application on the right. EFR Connect is a general-purpose Bluetooth toolkit available for Android and iOS. There are links to further information and downloads in the video description. I also have Thonny running on the left so we can see the debug messages being output. The first stage is to find our device in the scan results on the scan page. This is selected by clicking the scan button in the middle of the lower bar of the EFR Connect application. And we can check the device name that we're looking for by looking at the BLE short name displayed in the debug output. Clicking the Connect button next to the device will form the connection, and we can see that being picked up in the debug, along with the stopping of the advertisements. Next, we need to scroll down to find the immediate alert service and click the down arrow next to more information to see all the characteristics within the service. If we click the right button underneath the alert level, we can select a mild alert from the drop-down and click Send to transmit it to the device. Our target device now starts playing the mild tune, flashing the mild LED, and we can also see the changed alert level in the debug output. To cancel the alert, we can repeat the process by writing none to the alert level. And once again, the tune stops, the LEDs return to the idle pattern, and a debug message is output. Let's check the cancelling of alerts by using button presses. First, we'll set a high alert level as we did before. And now we can press any button on the device to cancel the alert and stop playing the tune. And once again, we can see that the alert has been cancelled locally in the debug messages, and we've returned to the non-alert state. Finally, I can exit from the device information page and click the disconnect button next to the device to close the Bluetooth connection. And we can see in the debug that the disconnection has been noticed and we've started advertising once again. So there we have it. We've created a Bluetooth Find Me target device in CircuitPython. In the next step, we'll add more code so it can also operate as a simple locator. Back in Thonny, I have the Step 3 files open in the Files tab for Step 3. The only changed file here, compared to the previous step, is the App.py file. I already have it open, so let's work through the changes. First, we have a new constant for a timer we will use while in the locator mode. In this mode, a Bluetooth scan will be started every second as set by this constant. Next are some minor changes to the initialization function, starting with an updated debug message reflecting the new functionality provided by this step. Then we create a new tick timer that will be used when in locator mode. It's not started here, we're just creating an instance of the class to use when we enter locator mode. The final initialization change is the addition of a new value in the Bluetooth dictionary. This will be used to store the alert level to be set when running in locator mode. So this is the alert level we want to set in the target devices we find. As we boot up into target mode, this is initialized to the non-alert level. The majority of the changes are in the main function. First, we have updates when a button is pressed, beginning with a check if the device is running in target mode, determined by the locate level value being set to none. In this mode, if the service alert state is set, then it is updated to cancel the alert. This is the same logic used in step 2, with a couple of extra preceding if statements. If an alert is not set and the high button is pressed, we swap to the locate mode at a high level, with similar logic applied if the mild button is pressed, swapping to locate mode with a mild alert level. When a button is pressed and the device is in locate mode, we return to the target mode by setting the locate level back to none and stop the locate timer. Next, the reading of the LED tick timer is moved up within the function and the locate timer is also read here. Then we have a test to check if we are running in target mode. In this case, the connection state, advertising, alert levels, driving of the RTTL class, and LEDs are handled in the same way as the previous step. Then we get into the new code that is used when running in the locator mode. First, if the radio is advertising, the advertisements are stopped. If the RTTL class is playing a tune, it is stopped. There's also a call to the RTTL main function to ensure it stops at the end of any note that is currently being played. This bit of code is for safety, as the button logic should prevent entry into locate mode when an alert level is set and an RTTL tune is playing. Next, we have some logic to determine if a location scan should take place to find other devices operating in the target role. If the locate timer is not running, it is started with auto repeats. But we will make a location attempt in this first iteration instead of waiting for a period of 1 second before we start scanning. When the locator timer is already running, we only run the location scan when it has fired. If the device is going to make a location attempt and the locate level is still set, we start by turning off both the LEDs. Then a Bluetooth scan is started. Any adverts that are received that include the immediate alert service, have a short name present in the advert that includes the string find me, we will add to an address list ready for processing later. The scan is started with a timeout of 100 milliseconds. During this time, we'll remain in the scanning for loop, handling any received advertisements. When the scan times out, we make sure that we stop scanning. Next, we turn on the LED that corresponds to the locate alert level. This has the effect that the LED corresponding to the locate alert level is always on, but with a brief 100 millisecond off period every second. This is now controlled by the locate timer for the 1 second overall period, and the 100 millisecond timeout on the scan for the brief off interval. When in locate mode and in the loop when we're scanning, we can't use the LED timer and masks because the CPU is busy while the scan takes place. Next, we loop through the list of any addresses that we found and saved during the scan. We attempt to connect to each address and attempt to find the immediate alert service within the connected device. And within there, we then attempt to write to the alert level with the locate level that's being used by the locator device. Having attempted the write, we then do a disconnection before moving on to the next address. And we make sure that that disconnection is fully completed before we go around the loop again. This immediate connection and disconnect is unusual for a Bluetooth application. It's more standard to connect to a device during the scan and cancel the scan at that point, and then remain connected while data is exchanged. These are the kind of applications where changing data continues to be sent for applications like monitoring a heart rate sensor, for example. For this Find Me application, when we're in locator mode, there's nothing to monitor. We just want to quickly set the alert levels in any devices we encounter and move on to the next one. This is why, in this particular application, we make use of an immediate connect, write, and disconnect cycle here. Finally, if we end up here with an invalid locate alert level set, we revert back to target mode to get out of the invalid situation. I've connected to a new second board in Thonny. This time I'm using the Silicon Labs XG24 dev kit. We'll see it in use in a moment. This board is newly flashed with CircuitPython, so I just need to select the step 3 files and folders, including the library folder, right-click and select Upload to Root. As before, I need to allow any overwritten files. Next, I can close the open files from my local file system and open the code.py file that's on my new device. From here, I can click the Run button to begin executing our step 3 code. And as we had before, we can see the updated debug message. We can see the board has been initialized successfully, this time the dev kit board. We've got a new different short name for our device that's advertising, and we can see it's booted up into target mode and has started advertising. The newly programmed board, the dev kit board, is on the right hand side of the screen. This board has an RGB LED instead of separate LEDs, and I'm using the red and blue channels for the high and low LEDs respectively. It is therefore currently briefly flashing magenta using the red and blue channels, indicating it's in the target idle mode. The other board is the Explorer kit. It still has the software in it from the previous step, as I'm only going to use it in target mode here. For now, I'll leave it powered off. Let's put the dev kit into the locator role at the mild alert level by pressing button 0. We can see the change of role in the debug panel and that it has stopped advertising. The LED is now set to blue to indicate the mild locate level, with a brief off period when the scan is performed. Let's power on the Explorer kit for our target device. Once it has booted, we can hear and see that it has been set to the mild alert level. I'll press a button on the device in locator mode to return it back to target mode. As you can hear and see, the Explorer kit is still in the mild alert state. Exiting locator mode on the dev kit does not cancel the alarm in the target device. I need to press a button on the target device to do that. You may also have spotted debug messages scrolling in Thonny as the locator device repeatedly connects, writes and disconnects from the target device. Now let's activate a high alert level by pressing button 1. This time the locator's LED is using the red pattern and the high tune is playing on the target device. Let's cancel it by pressing a button on the target device again. Well, it doesn't cancel for very long. The locator device is continuously setting the target device back into the high alert state. To properly cancel an alert with the code in this step, we first need to return the locator device back to target mode by pressing any button. And then we can cancel it locally on the target device. This code might work well if we want the locator to be very persistent in activating alerts and forcing the user to cancel on both the locator and any found devices. But for general use, it is somewhat clumsy, though at least we know the basic locator role functions are working. Let's continue into step 4. In this final step, we'll address the shortcomings in the way the device is operating in locator mode by limiting the number of writes to the alert level of any found devices to 3. This will prevent the locator device continuously setting an alert level in a target device, even where the alert has been cancelled locally. We'll also add a new state to transition from locator mode back to target mode. While in this new state, the device will attempt to clear alerts in the target devices it activated whilst it was locating. Of course, if the locator has moved out of range of any of those targets in the meantime, this may not be successful. But overall, it will work as a more user-friendly method compared to having to cancel on both the locator and target devices in that order that we saw in the previous step. Once again, the only updated source code file will be App.py, and I have it open in Phony from the Step 4 folder. The changes start with a new alert level cancel constant. We'll be using this for the locate level value while we cancel the alerts. Though keep in mind it is not an actual alert level that can be set in a device. We also have a second new constant, locate count max. This is used to set the number of attempts to write to a target's locate level, both when raising an alert and when cancelling alerts. Next, in the App.init function, once again the initial debug message is updated to indicate this is the advanced locator software. Then we add 2 more elements to the BLE dictionary. A new dictionary to store the write address and write count for each address we encounter while in locator mode, and a counter to count the number of cancellation write attempts. Let's move on to the main function. First, we have a reset of the locate counts dictionary and the cancel count value when entering high locate mode due to a button press, and the same when entering mild locate mode. These ensure there is no stale data from a device being in locator mode previously. Next, there are some changes when a button is pressed in locator mode. Instead of simply setting the locate level to none, we now set it to the new alert level cancel value. We also set the locate cancel counter value to 3. This will be decremented with each cancellation attempt. Also note that in the previous step we stopped the locate timer in this bit of code. In this step we'll leave it running and use it to time cancellation writes. Next we move on to changes when scanning in locator mode. Previously we stored a list of addresses in a local variable for each individual scan. This is now removed as we're going to maintain a list of found devices with write counts across all scan attempts whilst in locator mode. So when a new device is found that is not already in our locate counts dictionary, we add a new element to the dictionary using the address as the key and set the value to 0, which will be incremented as we count the write attempts. The next set of changes are to the loop that works through discovered devices, setting the alert level. We now loop through the addresses that are stored as keys in our locate count dictionary. These are all the addresses we have found whilst in locator mode, rather than the addresses that were found in the single scan that we did in the previous step. But we only connect and transmit the alert level writes when the count is below 3. And of course, we increment the count for that address if the write is successful. So this bit of code limits the writes to discovered target devices to 3, allowing the local cancellation on the targets to be effective after all 3 writes have been made, and usually this will be after 3 seconds. Next, we need to deal with cancelling alerts when the locate level is set to cancel. This code is very similar to setting alerts, but with a few minor differences. Both LEDs are turned on and are left on to indicate cancellation is in progress. The decrementing counter for transmitting cancellation rights is checked. If the check is passed, we work through the found addresses in our locate counts dictionary. And for any devices we wrote an alert level to, we connect and write an alert level of none to cancel any sounding alerts. Once we come out of the loop through the addresses, the cancel counter is decremented. When all of the cancellation attempts have been made, we then return to target mode by setting the locate level to none, resetting the locate data, and stop the locate timer running. The final change is another reset of the location data if the device ends up in an unknown state in Locator mode. We are now ready to upload the final version of the software and try it out. I've connected to a SparkFun board this time, which has a clean install of CircuitPython. So I'll select the files, right-click and select Upload to Root, once again allowing it to overwrite code.py. I'll close the open file from my local file system, open up the code.py from the SparkFun board, and click the Run button to make sure it's running. Checking the debug output shows we're running the new version of software, this time on a SparkFun Thing Plus board. Step 4 software is running on the SparkFun board on the left-hand side. Currently it is in idle mode with the onboard blue LED acting as the mild LED and the external white LED as the high LED. The Explorer kit in the middle and the dev kit on the right are still running the software from the previous steps, but I'll only be using them as target devices. Let's start by activating a mild alert. As you can hopefully hear and see, the two target devices are now in the mild alert state. It's a bit noisy with both boards sounding, so I'll turn them off locally with a button press. The SparkFun board is still running in Locator mode, but it is not reactivating the two target devices. I'll take it back to target mode by pressing a button, but both LEDs will remain on for 3 seconds while it tries to cancel the alerts it previously set. I'll test cancelling from the Locator device next, and I'll use the high alert level this time. Once both target boards are sounding, I can press a button on the Locator board to place it into cancel mode, with both LEDs coming on while the alerts are cancelled. The SparkFun board that was acting as a locator has now returned to target mode. There is also lots of debug data output by the locator as it activates and deactivates alerts in the target devices. So that brings us to the end of this Silicon Labs Dev Lab. We've gone through 4 steps, starting with simple hardware and adding in Bluetooth to create a Bluetooth Find Me device that supports both the target and locator roles. As a reminder, you'll find links to the resources that I've shown during this Dev Lab in the video description, including the GitHub repository that has the source code and wiring diagrams. Thanks for watching.